Hey guys, Mr. Smith here. Back in the dungeon where I started off the semester. Just it's a quiet place in the school for me to shoot video content. So here we go. Today we are doing our fourth lesson of Unit 6. We're looking at what we call the power law of logarithms. And as a bit of a motivation onto why that's useful, consider the following scenario where we invest some money, $100, in an account that pays 5% interest compounded annually. That just means that the 5% interest is calculated and added on at the end of the year. You can model how much you have at any given time throughout the year by the exponential function a equals 100, the initial value, times 1.05 to the power of t. This is a typical exponential function maybe would have created in your grade 11 course. And things you did in your grade 11 course would be, after 5 years, how much do I have? Plug in t equals 5 and solve for a. After 10 years, how much do I have? Plug in for t, solve for a. But what if you want to know how long it would take your investment to grow to a certain amount? Maybe you had a savings goal or something. Let's look at a simplified scenario of that and just ask how long would it take for our investment to double? That would involve plugging in 200 for the value of a and solving that equation for t. Now, when you divide both sides by 100, this equation would reduce to 2 equals 1.05 to the power of t. And we know that by rewriting this in log form, that t would be equal to the log, our base is 1.05 of 2. However, right now, we don't have a tool to do this on our calculators. Our calculators can only do logs base 10 using your log button. So today, we're going to learn how to calculate these on our calculator and develop a rule to help us solve equations like this. So we've got to, first of all, to motivate the power law of logarithms, a little bit of a numerical investigation for you guys to do. Simply want you guys to evaluate these 5 logarithms. We're doing the first column to begin with. Log 2, log 4, log 8, log 16, log 32. On your calculators is fine. 2 decimal places should be enough for us to get the idea of what's going on here. So I'm going to pause my video recording. I'm going to do this as well, and I'll check back in with you guys when I'm done. All right, so I've done mine. Hopefully you guys got the same values, and 2 decimal places is enough to hopefully for you guys to see a pattern. What you'll note is that we got log base 2 is about 0.3. This means that 10 to the power of 0.30 is approximately 2. The log of 4 was twice as much. The log of 8 was 3 times as much. The log of 16 was 4 times as much, and log 32 was about 5 times as much. And each of these guys was just a bigger power of 2. 8 is 2 cubed. 16 is 2 to the power of 4. 32, 2 to the power of 5. And it looks like the log of these different powers of 2 is equal to whatever that exponent is, n, times the log of 2. It appears that way, right? Log of 2 squared was as 2 times log 2. The log of 32, 2 to the power of 5, was about 5 times log 2. Does something similar happen? And maybe it was just a coincidence. Does a similar thing happen when we look at powers of 3 instead of powers of 2? So our next column is very similar. This is the log of 3 squared. This is the log of 3 cubed. The log of 3 to the power of 4. And the log of 3 to the power of 5. Can you guys do those 5? 2 decimal places should be fine to get the idea. And see if a similar rule kind of falls out. So I'm going to pause my video recording here and do that as well. I'll check in with you guys in a second. All right, so I got these values to 2 decimal places, which is kind of enough to hopefully see the rule. Look at log 3. Log 3 was about 0.48. The log of 3 squared, or the log of 9, was about 2 times that. 0.95 is roughly 2 times 0.48, and we did some rounding. The log of 3 cubed was about 3 times the log of 3, and it seems like this kind of the same thing happens. It appears that the log of 3 to the power of n is equal to n times the log of 3. So it appears it wasn't just coincidence. This rule worked with the base of 2, and it works with the base of 3, and it actually works for any base. Um, uh, Here we use the common logarithm of log base 10. This rule actually works with any base. And so right now, we're going to state this in its most general form, and then we're actually going to prove it. So the power law of logarithms says this, that log base b of x to the power of n. So again, in our little investigation, our base b was 10, but actually this works with any base, which is pretty neat, is equal to, you can actually kind of like bring the exponent down in front, is equal to n times the log base b of x. So that's pretty neat. Now, as usual, this is only defined when we're using a base that's positive, just like exponential functions. And the base can't be 1, though. And this works for if the power, the base on the power inside the log x has to be positive as well. So there are some conditions for this. Also, n has to be a real number. So there are some conditions for sure. We can't do this with negative bases inside the log because that would give you as we know, the domain of the log function is x has to be a number bigger than 0. But yeah, that's really a neat rule that kind of falls out here. Not really obvious until you start playing around with it and see. We can actually prove this. It's not too bad to prove using a little bit of algebraic reasoning. So we're going to start off here. We're going to let's call it w equal log base b of x. Now we know we can write this in exponential form as x equals base b to the power w. Now our rule was a power law, and we had x to the power of n. So I'm going to raise both sides to the power of n. So x to the power of n equals b to the power of w raised to the power of n. Go up here for more space. And I'm just going to use our power rule for a power of a power. X to the power of n equals b to the power of w times n. And at this point, let's rewrite this in terms of logarithms. So our base is x, our exponent, on the left-hand side, our base is b, and our exponent's wh. So or w times n. So I can write this as the log base b of x to the power of n is equal to w times n. That's just rewriting that exponential in terms of a logarithm. And that's almost our rule. It basically is rule, but remember that early on in the question that we said w was equal to log base b of x. So the log base b of x to the power of n equals log base b of x times n. And we've basically shown it, right? It's just the way we stated the rule, we have the n out front. So pretty neat. So this is the power law of logarithms. And we're just going to apply it today, use it in a few different contexts, use it to solve some equations. Very, very helpful. All right, so let's look at part A here. So We're just going to apply this a few times. All right. Now, we actually can already do things like A using rules we already have. So for A, I might do it up here. We have two ways we can think about this one. So method one, we can think about using a common base. What do I mean by that? So we can write log base 3, 9 to the power of 4. We can write 9 to the power of 4 as 3 squared to the power of 4, because 9 is 3 squared. And we can simplify this, log base 3, and then 3 squared to the power of 4, that's 3 to the power of 8. And then we actually know this answer. We actually talked about this property in a previous lesson. But what this is saying, log base 3 of 3 to the power of 8, is 3 to what power gives you 3 to the power of 8? Well, the answer is just 8, right? So we can do a question like this by using a common base. We could also do this using our power law. Squeeze that in there. So what would that look like? So we have log base 3, 9 to the power of 4. Well, using our power law, this is equal to, we can bring down that 4. This is 4 times the log base 3 of 9. And, most of you guys hopefully shouldn't need to rewrite 9 as 3 squared to see that log base 3 of 9 is just equal to 2. But if you need it, you can rewrite it this way. You can show this extra step. 9 is 3 squared. 3 to what power gives you 3 squared? Well, 3 to the power of 2. Probably could have gone there right from this first line. But yeah, you get 8 either way, whether you just use a common base or whether you apply the power law first. So let's try a couple more. And let's try using method 2 because, method 2, applying the power law, just keeps the number smaller, more manageable, generally involves less calculations. So let's do log base 2 of 8 to the power of 5. So using our power rule, bring down the 5, log base 2 of 8. You can go arguably many of you just understand, okay, 2 to what exponent gives me 8, 2 to the power of 3 gives me 8, and that's 15. Some of you may wish to show an intermediate step where you reason out, okay, 8 is 2 to the power of 3, and then 2 to what power gives me 2 to the power of 3. You get 3 either way you slice it. So my recommendation at this point would be, can you pause the video and give C and D a try on your own, and then unpause when you're ready. I am going to continue. So hopefully you've had a chance to look at those. So the log of 0.001 squared. Using our power law, 2 comes out front, log 0.001. Remember, if we just see log, we know the base is 10. 0.001 is a power of 10. It's 10 to the power of negative 3. And so we have 2 to the power 2 times negative 3, negative 6. All right. And let's see how you guys did for D. D was log base 5 of the root of 125. So that one was a little bit of a had a little bit of a twist because the root of 125 isn't a power, but we can write it as a power. This is log base 5 of 125 to the power of a half, like you guys learned in your grade 11 math course. And now we can apply our rule. This is 1/2 times the log base 5 of 125. Again, some of you guys can just see, okay, 5 cubed gives me 125. But if you want to show that kind of show a few more steps. You can write 125 as 5 cubed, and then it becomes really obvious that it's 1/2 times 3, or 3/2. Squeeze it in there. Showed a lot of steps there. All right. So a bit of experience applying our power law of logarithms. So let's continue. Let's revisit the kind of motivation we talked about earlier on. So remember when we were investing $100 at 5% interest compounded annually, if we wanted to know how long it would take for our investment to double, we wound up with the equation 2 equals 1.05 to the power of t. When you find this time, this is called the doubling period of an investment. Let's find the doubling period for our scenario. So our starting point is 2 equals 1 point. Why can I not read today? Our starting point is 2 equals 1.05 to the power of t. Might actually zoom in a little bit more, help with the fine motor skills. There we go. And so here we're going to apply our power law of logarithms to solve an equation. And this will motivate doing it even quicker on our calculators. But let me show you guys what we're going to do. We're going to take the logarithm of each side. The log of 2 and the log of 1.05 to the power of t. So why do we do that? And we're taking the common logarithm, log base 10. So why do we do that? Well, one, like log 2 is actually something we can do on our calculator. Calculators have our log button. And we can actually take the right-hand side and get the t out of the exponent. This is the beauty of this power law of logarithms, is because this gives us a way to access that variable in the exponent. Is equal to t times the log of 1.05. And we can isolate t. T is equal to the log of 2 divided by the log of 1.05. And our calculators can handle this. We have our log buttons. Log 2 divided by log 1.05. And so I got about 14.2. I'm going to make a little concluding statement. It'll take about 14.2 years to double. This is fantastic news because now we don't need systematic trial and error to solve equations that have an exponent in them. We can take the log of each side and use our new rule to get the t by itself. Very cool. This technique we used here, and I'm going to combine it. If you recall earlier, we said, okay, the solution to that equation is going to be the log base 1.05 of 2. And we just showed that the solution was equivalent to log 2 divided by log 0.5. So I'm just improvising a bit on the fly here. What we showed indirectly here is that the log of 1.05 of 2 was actually equal to the log of 2 divided by the log of 1.05. This actually, the power law for logarithms gives us a tool to take a log in any base and turn it into log with a base of 10 so that we can just use our calculators. So that's pretty cool. So I'm going to show you guys, we're just going to kind of generalize this technique first, and then we'll state the change of base formula afterwards. So in general, so let's let x equal to log base b of m. So we have some log we want to evaluate, like log 1.05 of 2. We want to evaluate this. How can we do it? Well, we rewrite this in exponential form. So the base is b, the exponent is x, and the result is m. And now let's take the log of each side. So we have the log of b to the power of x is equal to the log of m. Using our rule, our power law, we can bring down the x. So we have log b. This is equal to log m. But the log doesn't have an O anymore. Log m. And when you isolate for x, you get x is equal to log b divided by log m. Of course, remember that x was equal to log base b of m. So this is pretty cool. You know what? I have the order mixed up there. If you notice that, sorry about that. This would be log m divided by log b. So this gives us a way to evaluate any logarithm at all using our calculators. Log base b of m is the log of m, the log of the inside, divided by the log of the base. This is great news. We can summarize this. This is called the change of base formula. So we'll just get it down here. Log base b of some result m is equal to log of m divided by log of b. And of course, we have the usual restrictions. Since we're doing logs, you can't have negative inside a log. So m has to be bigger than 0, b has to be bigger than 0, and of course, b can't be equal to 1. Why can't b be equal to 1? Because then the log of 1 would be 0, and you'd be dividing by 0. But m could be equal to 1. Yeah, so very useful change of base formula. Let's test out this new technique to evaluate these two logarithms on our calculators. And before today, we would not be able to do this. So let's look at A. So log base 5, 17 equals what? Remember, this is like saying, okay, 5 to what power gives you 17? Not obvious at all, right? But using our new rule, we can write this as log 17 divided by log 5, which we can do on our calculators. Log 17 divided by log 5. And so to two decimal places, I got 1.76. And you can try that out on your calculator. You can always check these. 5 to the power of 1.76 should be very close to 17. It's 16.9897, blah, blah, blah. So yeah, it checks out. Let's try it with B. Log base 1/2 of 10. So using our new technique, that's equal to the log of 10 divided by the log of 1/2, which our calculators are more than happy to do using the log button. You give it a try as well. I got negative 3.32 approximately, and we can check this out. So the base is 1/2, so you can do 1/2 to the power of negative 3.32, and according to this, it should give us 10. Yeah, because I got 9.9866 because of our rounding. So yeah, it does equal 10. So very neat, very, very, very neat. So now again, guys, remember, we don't have to use trial and error anymore for these logs with different bases where the answer is not obvious. We can now do logs with any base on our calculators. And to finish things off, this just gives another way to graph logarithmic functions with different bases. So let's say I asked you guys to draw the graph of log base 5 of x. Going back to lesson 1/lesson 2, we could draw this by drawing the graph of 5 to the power of x, which goes through 0, 1, and 1, 5 as some anchor points. I guess it also goes through negative 1, 0.2. The graph looks something like so. And then we know that log base 5 of x is the inverse. So I'm just going to sketch in the line y equals x. Just going to add a dashed line for that. And then reflect those points. So -1 is 0.2. We'll go to 0.2, -1. 1, 0 goes to 0, 1. And 1, 5 goes to 5, 1. There we go. So this is y equals log base 5 of x. Now, our new rule that we just developed can actually help us graph these using graphing technology. So the key idea, we're going to graph it in Desmos in just a second, is that we can take y equals log base 5 of x. And a program like Desmos is like your calculator. It doesn't have a log button for all the different bases. It has log for base 10. But we can write this function that's in base 5 in terms of logs with base 10. We can write this as, using our new rule, as log x over log 5. And I'm just going to quickly head to Desmos just to check that out. All right. And so we're going to graph log x. So as you guys can see, that's our log function. It doesn't go through the points we need it to go through. We need it to go through, let me just add a table. This will actually be helpful. We need to go through 0.2 and -1. And we need to go through 1, 0. And we need to go through 5, 1. So the way we're going to do that is we're going to graph the function log x, and I'll put that in brackets, log x, and we're going to divide it by the log of 5. And you can see that it actually is an equivalent graph. It goes through the same points that the inverse of 5 to the power of x went through, and it fits perfectly. So hopefully you guys are convinced that we can graph log base 5 of x, or any log with any base, by using this new rule. So really, really useful stuff we've done today, guys. And that's it. So what we learned today, we learned power law of logarithms, and we use that to solve equations and to develop this really important change of base formula. This is really useful to solve equations, evaluate logarithms that we previously couldn't do on our calculators, and also to graph log functions with any base. If you're trying to use Desmos can only do log base 10, but now we can use the change of base to graph anything we want. All right, so I've got some suggested practice for you guys. Hopefully you guys enjoyed that lesson. I enjoyed giving it. In the meantime, stay well, guys. Please reach out if you need a hand. We'll see you soon.